Okay, so we're going to continue on and we just have one last part in module 1 to look at. So if we peek over at our learning plan, we're going to pull up the PowerPoint presentation, the part 2. And then what we're going to do is we are going to scroll down, kind of get rid of my chat here. We're going to scroll down. Maybe I'll just minimize the chat for right now. We're going to scroll down to where we see tangential and normal components of acceleration. So all of you have had kinematics already. And in kinematics, we know that as we have a point that revolves around a fixed center, we have an acceleration that is going to occur. We remember that we had two components to that acceleration. There was a straight line component, which was called the tangential component of acceleration. And then we had a normal component of the acceleration. So in this section, we're going to be kind of looking at that a little bit more in terms of the problems that we're looking at. So as we look at tangential and normal component, first of all, let's look at the normal component of the acceleration. So the normal component is going to be acting along the radius and pointing towards the center of rotation. So if we're analyzing a point, for instance, and we would be looking at the normal acceleration component of the acceleration, okay? That means that the tail of that vector is going to start at the point and it's going to point down towards the center of rotation wherever that may be. That's the normal. It's kind of like if you would pulling it into the curve, okay? The other component of acceleration is going to be tangential acceleration, okay? And tangential acceleration is going to be acting perpendicular in the direction of, perpendicular to the radius, but in the direction of the acceleration. So when we look at acceleration, we can have really two conditions. We're either speeding up or we're slowing down, okay? So for instance, if we are increasing our velocity and we're speeding up, that means that the acceleration is going in the same direction as velocity, okay? And we saw that again in kinematics. But if we have a condition where we're decelerating or slowing down or something is braking, our velocity is still going to go in, for instance, a straight line motion, going in a x direction, positive x direction. But because we're slowing down, that acceleration, if you would, is impeding motion. And so it is actually going to be along the same line of action, for instance, horizontal, but pointing in the opposite direction of the velocity, okay, because it's slowing it down. Now, to calculate these values, so the total amount of acceleration, because of the fact that these are 90 degrees to one another, okay, so our normal is pointing down towards the center of rotation, and our tangential is perpendicular to that. Those are if you would, the two sides of a right triangle. So let me see. I forget. I'm gonna peek ahead. I'm going to go, yeah, they don't have an illustration here. So what I'm going to do is I'm actually going to draw underneath my camera here a little quick illustration of tangential and normal. So if we have a center of rotation, for instance, okay, and we have, I'm going to just kind of draw a link, kind of remembering from kinematics, okay? And if we have this point right here, we'll call this point A, for instance, all right? And if we know that this is rotating around, so it's going to have, if you would, a value for W. So it is going to have both velocity and acceleration. Now the velocity, we know the straight line component of the tangential velocity is going to go in the direction of rotation, and we're going to call this tangential velocity, 90 degrees to that radius of rotation from that fixed center, okay? But the acceleration that occurs, and that's what we're talking about here, the acceleration is going to have two components, and there's going to be a resultant then because of those two components, all right? So this is velocity here, those two components of acceleration. Now, because this velocity is on this line of action, our tangential acceleration is going to be along that. If this happens to be speeding up, our acceleration is going to go in the direction of the velocity, the straight line velocity component. Okay, makes sense? But if we're slowing down, okay, if we're slowing down, I'm just going to kind of get rid of that, then our acceleration tangential is going to go in the opposite direction of the straight line velocity, okay? Remember, we can have two conditions of acceleration, speeding up or slowing down, or no acceleration, constant velocity, right? So, so the tangential is always going to be perpendicular to the radius, but depending on if it's speeding up or slowing down, it'll either be in the same direction of the straight line velocity or opposite if it's slowing down. Okay. Now the other, oopsie, let me go back here. I'm sorry. Oh, no problem. That's okay. Understood. So then the other component of acceleration is that normal component. The normal component of acceleration is always going to be from the point that we're analyzing, and it's going to point towards the center of rotation. So if this is our radius of rotation, this is going to be the direction of that normal acceleration. There is no acceleration that's going to point out. It's kind of like the component that keeps it in the circle, okay? All right. Now, the total acceleration then, the total acceleration is going to be the resultant of those two forces that are 90 degrees to one another. So if we draw our little construction lines, and from that point of application, this is going to be the total acceleration, right? And we can find that through Pythagorean's theorem, what the magnitude of that will be. And that's what we see on that previous slide. Okay, so right here, this equation for total acceleration, or just acceleration of a point, is going to be equal to the square root of the normal component of that acceleration squared plus the tangential component of that acceleration squared, which means that's using Pythagorean's theorems because it's a right triangle, because the tangential and normal are 90 degrees to one another. Okay, so that should also be relatively relatively familiar to us. Okay, now as we look at calculating their magnitudes, okay, the magnitudes are going to come from these two equations. The normal acceleration is going to be equal to the velocity squared, so that's going to be the straight line velocity component, divided by, now I have p, this is actually phi as a Greek letter in our examples, okay? So I just put p here just because when I put it in. So p, or phi, is going to be the radius of the curve, or the radius back to the center of rotation, okay? When we have things like velocities on projectiles, there's not a set center of rotation, but there is a radius of that curve. And that's going to be a variable that we're going to want to it's either going to be given in a problem or we're going to want to solve for it. Okay. So that's that value. And then the tangential is simply going to be, it's that straight line velocity component, or it's the straight line acceleration component. And it's going to be the change in velocity. Okay. Because it's accelerating, it's either speeding up or slowing down. So we want to know, okay, the difference between the initial and the final, or the original and the final, divided by the time that it took us to get there. So that's this equation here. Now, what I have done on my equation sheet, I've been kind of pulling mine in and out. My expectation is, and something that you're going to be handing in as part of your practice problems, not only are you doing these sample problems that we're following along in the chapter and we're doing together, but part of your practice problems is to hand in the equation sheet that you've been creating, okay? I added a little section, and I'm always happy to share these with you, just if you want ideas about what you want to add. The ones that I've been finding come in handy. So this is curvilinear motion, what we're just talking about, which is really the last section that we're going over here. So this is what I added to my section here. So this is the tangential component. This is the normal component. And then this is the equation for the total acceleration using that Pythagorean theorem's form. And then phi here refers to the radius of the curve. Okay, and that you see down in the denominator of the normal component of acceleration. And then I just put little notes of the tangential is going to be perpendicular to the radius in the direction of acceleration. So again, going along in the direction in velocity, pointing with the velocity when we're speeding up, and it's going in the opposite direction of the velocity when we're slowing down or decelerating. But the normal is always going to point from that center down towards the center of rotation or the center of the curve that's created from the path. Okay. All right. So I'm going to be referencing back to this as we, do the next two examples. So we're going to do two examples, kind of working with this. And then it'll kind of bring us to the end, and I'll take any additional questions or go over the homework that you have assigned here as well. So keeping this in mind, let's look at the two problems that we are going to be looking at here. So we're going to be doing sample problem 1116 in our book. And then we're also going to be doing the next one, which is going to be 17. Okay. So this is found on, if you're looking in your textbook, this is found on page 697. Now, something I want to ask everybody, hopefully, if you have a chance, if you don't mind, could you just check your availability and your access to the textbook? Has everybody been able to get in and out? Okay, currently. Last night in statics, we were using a McGraw-Hill, similar situation, and all of a sudden, most everybody lost connection, but it seems like it's been restored. So I don't know if there was a little time frame when we were down and we happened to be in that. I just wanted to be sure that yours is working, Aaliyah. Thank you so much. I just want to be sure that everybody has access to it, because what I did do then last night is I made PDF copies of the pages that they needed and then uploaded those. So if we do need to do that, I certainly am happy to do that. And that's one of the downfalls. The main advantage of an ebook is that I'm telling you, it saves you guys a lot of money in terms of buying a physical textbook. They make it so much more affordable. I believe it's $30 to $40 more that you just pay for the access during the class. Yes, you don't get the textbook to keep then forever, but it does save a lot of money. If you did, I just want to remind you, if you did want the hard copy, remember, of this textbook, it would be in three-hole punch form, or in like loose leaf form. You'd have to put it into a three-ring binder. Those are available in the bookstore, probably for a limited time yet, maybe a week or two, and then they'll, kind of not offer that. But if you do like that physical copy, that's a good alternative, and that also is about $30 to $40. So anyway, but we have to deal with technology on ebooks. So if you do have any issues, let me know right away. All right, so let's look at this problem. It says here that in sample problem 1116, we have a motorist is traveling on a curved section of the highway that has a radius of 2,500 feet at a speed of 60 miles per hour. The motorist suddenly applies the brakes, causing the automobile to slow down at a constant rate, okay? Knowing that after 8 seconds, the speed has been reduced to 45 miles per hour. Determine the acceleration of the automobile immediately after the brakes have been applied, okay? So as we look here, what we want to do is I like to kind of look at the problem, and this is what we have here. Now, first and foremost, we have to get everything in the same units. So you're going to notice that they're giving us the radius of the curve that the road is taking is in feet. And then we've got our speeds in miles per hour. So what we're going to do is step number one is going to be to convert those speeds into feet per second so that the units are going to be consistent so that we end up with, the information that we need. Then the next thing we're going to do is, because this is going around a corner, we need to find the total acceleration. So it's just asking for the acceleration, but because this is going around a corner and this is curvilinear acceleration, we know that we have to calculate a normal and a tangential component. So we're going to be looking to these normal and tangential equations to solve for that total acceleration. Okay. All right. And then because the acceleration is a vector, we're also going to be finding out what is that angle that it's at as well. Okay. So that's the process. So that's what we're going to be looking at. So we are going to start by kind of getting in the information at the top here of what we know and what we're going to try to find. So this is sample problem 1116. And the information that is given to us, okay, is it gives us that radius of the curve, okay? So phi, okay, P in my slide, but phi is equal to 2,500 feet, okay? Now, this book tends to use VO for original velocity. So whatever velocity you're starting out at, if you have, like I have in the past, I most often would refer to as the initial velocity. So VO and VI are the same thing. I'm going to use VO just because I want to be consistent with what the book offers. So if you look back, you can see that those are the variables that they use, but it is the same as initial. And that's 60 miles per hour. And then we've got our V final because we slow down to 45 miles per hour. And in order to do this, the time to go from 60 to 45 is going to be 8 seconds. Okay. Now, up here, I like you to put your units. I told you as we go along, because there's a lot of variables to deal with, especially in dynamics. And sometimes it can get a little, because it's physicsy related, it can get a little confusing. Is this a mass variable, or is this meters? So sometimes leaving the units off actually is a little bit easier, but that means you have to be consistent with your units at the top. So we're going to be doing a little bit of converting. So make sure up here you're putting your units up here so then we know what we're going to. And then as far as what we want to find, we want to find what the total acceleration is, okay? And I like to right away, if I know the equation for that, I know the acceleration is going to be equal to the square root of the normal component squared plus the tangential component squared. And we're going to take the square root of that addition to find the acceleration. So as we look here, you know, we got to kind of start with the variables that are in here using the information that we have given to us, okay? So as I said earlier, since we're in miles per hour and we have our distance in feet, and we know we're going to have acceleration in feet per second squared, right? We are then going to, step number 1, we're going to do some conversion. Okay. All right. I need a sharp pencil. So for our first conversion, we're going to take VO and we're going to find what 60 miles per hour is in feet per second. So you can go ahead and do that. I'm going to do it on the side here, and we're just going to make sure that we get the very same answer. So my VO is going to be equal to, remember, you want to set this up as 60 miles on top per hour on the bottom. So don't use the slash here, or don't use MPH. Oh, Jason, and it works fine. Christopher, thank you. Thank you for confirming that with the textbook. I appreciate it. Yeah, I think it was just maybe it was a little time frame where there was a little glitch going on. Because today it seems like it's working for everybody as well in statics. All right, so did everybody get original velocity or initial velocity as our 88 feet per second? And then your final velocity for the 45 meter or miles per hour at 66 feet per second. Okay. Yep. Thank you. Thank you. Thank you. All right. Cool. So once we have that, now we have our distance in our feet. We have our velocities in feet per second. So now as we use our time, our acceleration then is going to be in feet per second squared. Okay. So again, knowing that, setting things up appropriately. if you want to put the units in because you're like, I really like doing that. And you have more confidence in your final answer, which I totally agree. Feel free to add it. But like I said, I'm not requiring it just because it can really kind of clutter things up and it can also get confusing, especially when we have units that have the same types of variables. Okay. So now what we want to do is we want to calculate these two variables, normal and tangential, so that then we can put them in terms of their acceleration. So as we look here, I'm just going to start with the normal component of acceleration just because it was the first one that I put in there. So I can say that the normal component of acceleration is going to be equal to v squared over phi. Okay. Now in this problem, we're given phi. That's that radius of the curve, which is 2,500 feet. So we'll be able to put that in. So we know what phi is, right? Now the velocity here, okay? The velocity that they're looking at for the normal, we want it to be right, because the question is asking us, what is the constant acceleration that's going to occur right after they start putting the brakes on? So that means that this is going to be our original or initial velocity that we're going to use here. And if you would, you always want to kind of plan for the acceleration that is, if you would, the worst. And that's going to be our initial velocity is going to have the higher speed. So that's going to give us our larger value for the normal force. So we'll just put those values in there. Now, remember, we want to put in the 88 feet per second. Just put 88. You don't have to put feet per second if you don't want to. That's okay. I'm going to leave it off. It's hard for me to do that, but in the end, it does actually help a lot. And then my phi is going to be 2,500. Okay. So make sure that you square 88. You divide by 2,500. And your normal acceleration should come out to be 3.098 feet per second squared. Okay. I'm just going to put a little cloud around this because this is not one of my final answers, but it's going to be one of the variables I'm going to use in that equation for the acceleration. Okay. Then the other one that we have here is going to be the tangential component. The tangential component, okay, if we go back to our equation sheet, is going to be the change in velocity divided by the change in time. It's like our standard acceleration, straight line acceleration, because it is a straight line acceleration that is perpendicular to the radius of rotation or the radius of the curve that we're on. So we're gonna say, okay, that tangential is going to be equal to change in velocity over the amount of time that it takes to do that. This time is going to be the time to go from 60 miles per hour to 45, okay? But remember, we're not using these values. We're using these two values. Now, when we show this in its term, we know that the brakes are going on. So our final velocity in this case is going to be smaller than our original velocity, which is okay because we're going to end up with a negative value for the tangential component of the acceleration, which makes sense because it's going in the opposite direction or it's decelerating the motion. And then it's going to be the original divided by that time. Okay. So our final is the 66 minus the 88 divided by 8 seconds. Okay. So our tangential component should be a negative 2.75, and this would be feet per second squared. And again, just a little cloud around there because I'm going to be using it in the next equation for the total acceleration. Okay, any questions so far? All right. So then all we're going to do now is we're going to use this equation, Pythagorean theorem's form, to solve for the magnitude of that resultant force, right? But in this case, it's going to be the total acceleration. So that's going to be equal to the normal plus the tangential squared underneath the radical. So that's going to be equal to, my normal is 3.098, square that, and you could put the negative in here if you wanted to, but by squaring the negative, it's going to become positive anyway. So you can just write the absolute value. It doesn't change anything in terms of the acceleration. That makes sense to everybody? Okay. So now your acceleration should come out to be 4.14 feet per second squared. Now, again, make sure your final answer always has the appropriate units. And we know that acceleration is going to be distance divided by time squared. Okay, so feet per second squared. Did everybody get the 4.14 as you did on your calculators? Awesome. Okay, so piece of cake. These are a little bit more straightforward. I think there's not as many assumptions, or kind of, I call it plug and chug, you know, to get the answer. Now, the very last thing here, because acceleration is a vector, let's show what that would look like on the curve, if you would. So if we kind of go back to this point A, it's not really telling us, you know, where this is in terms of like around the curve or at what angle it's at. But what I'm going to do is I'm going to kind of go radius of, now this center is just the radius of the curve. Okay, so this is like my phi. We're going to call this car A. Just going to leave that there and I'll add A in a little bit. We know that it is going to be going, and I'm just sketching here, on a curve, okay? And along that curve, perpendicular to that radius, we have the line of action of the straight line, okay? We know that going in the direction of motion perpendicular to that radius, this is the velocity of car A, okay? It's 60 miles per hour and then goes down to the 45, that's fine. This is when it starts the curve, okay? So now if we want to show, and we will show, the direction of the acceleration components, that means that here's my radius of rotation, right? So my tangential is going to go opposite the direction of motion, but perpendicular to the radius, in this case, of the curve, okay? So this is going to be my tangential acceleration vector, all right? Then the normal is going to go from point A and it's going to point down towards that center of the curve, or center of rotation, if you would. So this is going to be the normal. So now I can put A there. Okay. So the total acceleration is simply going to be the resultant of those two forces. So this is going to be A, if you would, right? Okay. Now, this is a vector. We're showing lines with arrowheads on each one of these, okay? So if we wanted to find the direction, do you remember that this would be alpha or theta, however we'd want to call it out, and you can then add the direction. You're going to notice that's what they do on the very end of this problem, because fully defining a vector is also showing its direction, okay? I'm going to kind of skip that because magnitude-wise, because we're going around a corner, it's going to continue to curve. But in a problem, if they are asking for a direction or what the angle is, that's where it's coming from, okay? They're using then the tangent function to get its angle relative, really, to the tangential and the normal components, okay? All right, so that is problem 1116, okay? Any questions on that one? All right, so again, we started out, we had our variables, what we were going to find, and then we did our conversions as needed in this case, and then worked through the normal tangential and used Pythagorean theorem form to get the total acceleration here, okay? All right, so then let's look at the second problem that we have in this section. The second problem that we have is going to be sample problem 1117. And I think it's going to be easier for everybody to see it if we pull it up on the screen here, okay? So for problem 1117, they want us to determine the minimum radius of curvature, phi, on the trajectory described by the projectile considered in sample problem 1110. We did this one. We did this one the last time we were together, okay? So what I'm going to do is I'm going to pull out that problem. I did not grab it out. Hold on. I'm going to pull out that problem and kind of revisit what we did there, okay? And then that way we can use this information here. So going underneath our camera, okay, as you can see, The problem statement looked like this. I forget exactly what we wanted to know. We wanted to know what the horizontal distance was when it actually hit the ground over here. And I think what was the greatest elevation, okay? And so as we went through this process, we identified horizontal and vertical directions and components. And what we ended up with, if you recall, we had our point here. This was our velocity XO. That is going to be the velocity in the X direction original, okay? And we kind of followed that through the trajectory. So what ends up happening on here is so as that trajectory goes along, or as I think it was a stone that's thrown, it is going to take a path something like this, okay? And at the very top of that path, okay, is really the best place to look at that curve, okay? And the reason it is because if you recall, the only vector for the motion is the X component. At this point, the Y is exhausted. It is at the very tippy top, and the Y component of the motion here is 0. Okay, so the only velocity we have to deal with then is the horizontal component. So this is going to be VOX. Okay, and we know that to be from problem 1110. We calculated it. I'm going to go back to our little sample here. So here's VOX, and we calculated it to be 155.88 meters per second. Okay, so I'm going to identify that. So that's going to be 155.88 meters per second. Okay, and it's going in that direction because that's the way that it's being thrown. Okay, now if we look at the radius that's created, if you would, for that curve, this distance right here is phi, right? That's that radius. That's what they want to know for this problem. That's what they want to know for this problem. All right, now acceleration, because to find phi, as we know, phi is in the normal acceleration equation. So normal acceleration is going to be v squared divided by phi. So if we rearrange this, phi is going to be equal to v squared divided by the normal component of the acceleration. As we look here, we know that on a projectile, this horizontal vector of the velocity stays the same. It stays constant, right? From second to second to second. But the y changes. We said at the top of the trajectory, the y is going to be 0. What changes the vertical component of the velocity? Gravity, right? What's the acceleration of gravity? And which way is it pointed? Yes, we are in meters per second. So we are going to have 9.81 meters per second squared. That is the normal component because that's at the top of the curve and it's going to point down towards the center of that curve. So that's the normal component of the total acceleration. Does that make sense? Okay. So now that's going to be our value that we put down here. And because the only velocity that's occurring at this tippy top point, see why it's easier? If we were along the path somewhere else, we'd have a y component and we'd have to figure out what the total acceleration was. So that's why picking the very top, we only have to deal with the x because the y is exhausted. Okay, so this is going to be our VOX. So then we're going to use 155.88 squared divided by 9.81 meters per second squared. Now, you could put the negative in there, okay, but it's really absolute value because remember, we're just trying to find the radius right now of that curve, okay? So your phi should come out to be 2477 meters. And that's all they're asking for in this problem. Okay. I should put sample. I was too excited. I wanted to get into this so quickly. 1117. Okay. I can. So kind of looking at these relationships and, two different problems and, solving this time for the radius or the radius of the curve as opposed to the total acceleration. Yes. You could in a problem like this. Yes, yes. But if you were anywhere along the sides, then you would have to use, for instance, if you were down here, you'd have to use the y component to find the total velocity, which then would go in here. Yeah, yeah. So if it was even asking for a specific place along the curve, you would have to do that. Yeah. But the radius will be the same all the way along. Right. So no matter where you do it, and that's why if you do yourself a little bit of a favor and do the tippy tap of the trajectory, then you're kind of taking out of the process. Not that it's hard, but it's one, step or two that you don't have to do. All right, good question. So the question in the room was, can we pick anywhere along there? Technically, yes. All right. Give you a second to catch up. And then what we'll do is we will look at the couple, I think there's two problems that pertain to this section that you have part of your assignments. Okay. So let me put this back in place. So if we look, as far as this section, and as you know how this book is set up, it kind of goes over concepts, then it gives you problems to do, then it goes over more concepts. So trying to kind of break it up into this last section now, you'll notice that I picked two problems here. The first problem is 11-133, okay? It says determine the normal component of acceleration of a car traveling at 72 kilometers per hour on an exit ramp that has a radius of phi equal to 150 meters, okay? So it's looking at this diagram directly below, all right? Oh, I'm sorry, I think I have 3 problems assigned for you guys now too. So that's the first one. The next one is going to be 134, because I thought, I'm like, yeah, I did that roller coaster. It says determine the maximum speed that the cars on the roller coaster can reach along the circular portion AB on our track, which has a phi of 25 meters. Okay. And then the last one that you have is going to be 145. And that's a little bit further along chapter. And this one, I do that one. Let me just peek back because now I have it worked out, but I just don't want to say something I changed my mind on. Let's look at the application problems really quick. Oh yeah, 145. Okay, just wanted to be sure. So the last one here, 145, you have a golfer that hits a golf ball, okay? Gives you the initial velocity. They want you to determine the radius of the curvature of the trajectory described by the ball at a point A, okay, right here at the start, and at its highest point on the trajectory, okay? So that's the third problem that you would have. So with that, since now this brings us to the end of our chapter, our module, we've gone through all of the sample problems / practice problems that you need to hand in. So if we look back to our assignments, if you would, or the things that we need to hand in for module 1, I'm going to look at the learning plan here. After we go through all the things that we see here, which we have, you're now ready to hand in officially the practice problems and the application problems. Now, if we go to, oops, I picked the wrong one. Sorry about that. Practice problems for module 1. You're going to notice that I have a couple notes here. First of all, don't forget, even though we didn't officially, I kind of kept putting my equation sheet in and out, you do need to hand in the equation sheet that you generated for yourself based on the information here. I think it's important for you to have something that's meaningful to you that you create, okay? You certainly can use the same formatting I used, but you don't have to. And then if you recall, now this is a week ago already, so it's been a little while, but we generated that spreadsheet that had some different parts to it. For problems 11.1 and 11.2, you can do it all, pretty much all in the spreadsheet except for the actual derivations. But make sure if you're using the spreadsheet, clearly mark, highlight, label whatever you are using to answer the question. So for instance, don't just highlight something and I'm supposed to guess what it is, okay? So if we go to, underneath and we look at problem 11.1, just kind of remembering back to the beginning of our class, sorry, here we go. So for instance, we go underneath here, 11.1. You want to determine the position, velocity, and acceleration of the border at 5 seconds, okay? So those are really all on your spreadsheet if you filled it out with the different tabs like we had gone over, if you're kind of remembering back to that. But what I want you to do is you need to, if you would, highlight, but also in the cell next to it say equals the velocity at 5 seconds, equals the position at 5 seconds, equals the acceleration at 5 seconds. I want you to answer the question, okay? Also, I need to see what your equations were that you found for velocity and for acceleration because you're going to use those. So those are going to be hand calculations if you would, or if you wanted to put them in that spreadsheet on the first page where you can write each one of those, you can do it there as well. So if we do go back to the spreadsheet from the problem, remember, I on mine, you don't have to do it exactly the same way, but it's a good way to kind of get started. My first one was my time tab where you can fill in all of the equations for position, the one that's given in the problem, and then the derivative of position to get velocity, and then the derivative of velocity to get the acceleration, okay? And then these are what you're going to use to program and create the charts for position and acceleration and velocity. And then by highlighting here, for instance, at the 5 second mark, it's 18. But what I would want you to do is say equals, equals or acceleration at 5 seconds. So it just kind of gives me a label for what they're asking for. Does that make sense to everybody? So don't just highlight it, randomly highlight it and expect me to know what you're talking about. I want some sort of a label so that I know you answered the question. Is that helpful? Because I know some people were asking if you could do it all in the Excel spreadsheet, and kind of technically you can, as long as you label them appropriately, and I can easily see that. Okay. So for those first two, 11.1 and 11.2, primarily the spreadsheet, okay, that you can do. So number 2, it wants you to do that same thing, determine the time, position, and velocity and acceleration of the particle at or when the velocity is equal to 0 this time, okay? So again, you would want to highlight when those occur and then answer that question in the spreadsheet. So those are the first 2. And then periodically throughout, you're going to find that you're going to have opportunities to use the quadratic calculator and such. Now, when you're using the spreadsheet, you don't necessarily have to give me the file. Actually, I don't want the file unless I asked for it, if I'm kind of suspicious that something's not coming out right. But just give me screenshots then to show me the answers for the questions that it's asking for, okay, like we normally do. All right. And then you're going to notice the quadratic calculator here. And then you may find it, I didn't put it in all of them, but you might find it handy for a couple instances along the way on the other problems further along. Okay, I'm not going to go through each one of the problems at this point because I think we did kind of hit them in the other times that we were together. At least did a little bit of an overview, but those are just some reminders. Okay, now the other thing I want you to remind you of is that when you go to the application problems, I do have the final answers for you. So it gives you the opportunity that as you're working things, zoom out here a little bit. Here are the final answers that you should be getting for your problems. If you're not, then that's when you want to go back and kind of troubleshoot things and or ask questions here in class and say, hey, how did you get that? I wasn't getting that answer. Okay. So these are here for you. All right. So with that, that kind of concludes the information I wanted to give you for Module 1, Chapter 11. And now you're going to have the rest of the time this evening to make progress on the homework for Module 1. If you have any questions, I'm here to answer those for you. And then the next time we get together, we are going to start Module 2. Okay. So I'm going to stop our recording.